Okay, it seems we are ready for our next contributed talk, given by Projesh Nath Choudhury, and his topic is Blowup-polynomials and I suppose delta-matroids of graph.
Thank you. So today I'm going to talk about some new kind of construction arising from finite simple connected graph, which we call Blowup-polynomials of graphs, and which turn out to have some nice properties and connections. And this is a joint work with the previous speaker, Apurva Kare. So let us set some notation. Recall that a graph G is a pair B, E, where B denotes the set of paired vertices, and where B denotes the set of vertices, and E denotes the set of paired vertices, and whose elements are called edges. And in this talk, all my graph are finite, simple, unweighted, and the most importantly, is connected. So because the graph is connected between any two nodes B and W, there is a path which may not be unique. Therefore, look at any path of the shortest length, and I call that length as dBW. And it is clearly a non-negative integer, and it is equal to 0 if and only if B equal to W. And with this number, we form a B by B matrix called the distance matrix of graph G, whose BW element is dBW. And the determinant of distance matrix of tree studied a lot in the literature, and recall that tree is a connected graph with no induced cycles. In other words, a connected graph with n nodes and n-1 edges. So our work is motivated by two sort of classical facts. First one is algebraic, and to illustrate this, here is an example. Take two trees on same number of vertices, and clearly they are non-isomorphic. Now look at their distance matrices. Let us say for the first graph, vertex 1 is adjacent to 2, 3, 4. So obviously all the diagonal entries are 0, and the entries 1i are 1 for I equal to 2, 3, 4. And similarly, the vertices 2, 3, 3, 4, and 4, 2 are at a distance 2 from each other, and this gives distance matrix dt1. And similarly for path graph also. It turns out that both these matrices have same determinant. And surprisingly, this holds for all trees. And this was a result by Graham and Pollack in 1971. They proved that the determinant of distance matrix of tree on n nodes is a function of n, and it is independent of tree structure. So this provided us our first motivation. We wanted to look at other such families of graphs for which the determinant of distance matrix is a nice function. And the second fact which motivated this work is from spectral theory. Ron Graham again studied the spectral side of distance matrix of tree with Lovash in 1978. And one question natural to us is the following. Of course, distance matrix itself detect the graph. Just look at the entries which are 1, those corresponds to the edges. And once you have the edges, you have the graph. Now the question is, does the characteristic polynomial of distance matrix detect the graph G itself? Or in other words, do the eigenvalues of distance matrix recover the graph G? The answer turns out to be no. There exist non-isomorphic graphs. For example, these two graphs on same number of vertices. So the distance matrices are of the same size, and the characteristic polynomial agrees for these two graphs. But these two graphs are clearly non-isomorphic. Here is a vertex of degree 4, but there is no vertex of degree 4 in the first graph. So in particular, we can conclude that the characteristic polynomial does not detect the graph. And this gives us two interrelated motivations or goals. First one is to find a family of graphs GI indexed by some set I. For example, a family of trees on fixed number of vertices, such that the function I goes to det dgi is a nice function. For example, for this family of trees, the function is a constant function, which is purely a number in terms of k. And so we also want to find the other such family of graphs. And more importantly, this motivation help us to this motivation should relate to the other goal. This family help us to find a invariant which truly detect the graph G. Of course, distance matrix itself detects the graph, but we want some kind of polynomial invariant. So the goal of this talk is to tell you, indeed, these motivations are achieved with the same object, and that the object I want to tell you is called blow-up-polynomials, and the family here is called blow-up of graphs. And so let us begin with the family, then come to the invariant. So the key construction which will answer both of these questions and reveal many more interesting facts is the following. Take tuple of integers nb indexing by vertices, and I will call the new graph by G bracket n, which is again a finite simple connected graph. And the vertices are as follows. For nb, that integer that I have chosen, take that many copies of vertex b. Now connect all copies of a vertex, b to the all copies of another vertex w, if and only if those two original vertices b and w are adjacent in the original graph. Also note that a copy of a vertex b is not adjacent to another copy of a vertex b because I am lacking self-proof in the original graph. So let me give you some examples. First one is a path graph on 3 vertices. So just forget about the vertex C and look at the edge AB. Now create one copy of vertex B and 2 copies of vertex A. Now A is adjacent to B. The other copy, which I will call C, also adjacent to B. But A and C are not adjacent. So the path graph on 3 nodes is an blow up of an edge. Here are 2 more examples. One is that of a star graph. This is exactly same as saying start with an edge and blow up one vertex with n different copies and keep one copy of another vertex. And this is exactly the star graph. And similarly for cycle graph on 4 vertices, start with an edge, namely 1, 2. Now create 2 copies of vertex 1, namely 1 and 3, and 2 copies of vertex 2, namely 2 and 4. Now 1 is adjacent to 2, so 3 must be joined to 2. So 1 and 3 are adjacent to 2. But 4 is a copy of vertex 2, so 1 and 3 are also joined to 4. But 1 and 3 are copies of the same vertex, so they are not adjacent. And similarly 2 and 4. So these are some examples of blow up of an edge. And as I said, idea is to look at the determinant. Now look at the determinant of all these blow up families. And for these examples, one can explicitly calculate the determinant, and it's turned out to be this expression. And this is very clean and nice expression, and it consists of 2 parts. One is exponential of r plus n, where r is the number of copies of first vertex, and s is the number of copies of second vertex. And then a polynomial in r and s. Now note that, interestingly, distance matrix consists of 0, 1, and 2 only, and size of the matrix includes r and s. And this is the function of sizes. Now the question is, what is the determinant of distance matrix of graph blowups for general graph? Does it have something similar? And here is our first result. There exists a real polynomial, PGN, n denote the sizes. So the argument of this polynomial are sizes of the matrix. And the following happens. That DGN is first of all minus 2 raised to summation sizes minus 1 times some remaining factor. And the remaining factor is a real polynomial. And this expression holds for all tuple of positive integers. And moreover, this real polynomial is multi-affine in sizes with this constant term minus 2 raised to number of vertices in the original graph and the linear term given by this. In fact, we have closed form expression for every monomial. And the real polynomial PG, what we define to be blow-up polynomial of G, covers all sizes of blowups, and this attains our first goal. Here the family is parameterized by bold n, and the function n goes to det dgn is a nice exponential function times a multi-affine real polynomial, and so this covers our first goal. Now the question is, does this polynomial recover the graph G? So before answering this question, let me talk about a weaker question. Suppose G is an automorphism. So by the term automorphism, I mean look at the labeling 7 and 8. If that gets switched, the entire graph stays isomorphic. Similarly, 3 and 4 and 4 and 5. So if G has an automorphism sending a vertex B to W, then my blowup polynomial is semantic under this operation. Thus, we can conclude that the automorphism of G determines the symmetries of PG. Now the question is, if I know how my blowup polynomial is symmetric in the variable, can I understand the automorphism of G? And this is the weaker question. And the stronger question is, of course, does this polynomial recover the graph G, from which I could get at the automorphism of G? And answer turned out to be yes for both of these questions. The symmetries of blowup polynomial itself coincides with the automorphism of G, and more strongly, the purely quadratic or Hessian part of PG recovers the graph G. So these answers are our other goal also. We now do have a nice family of graphs called blowup of graphs, whose determinant behave nicely as a function of tuple of integers, and determinant themselves are multi-affine in sizes, and which turn out to recover the graph G. Any questions?
Is it possible that a graph can be obtained from two different graphs as a blow-up graph?
Sorry?
Is it possible that we can get one graph as a blow-up of two different graphs?
What?
So from a graph, we can blow up to some other graph, right?
Yes.
So is it happen that there are two different graphs which are not isomorphic, and they blow up to the same graph? Is it possible?
I think no, it's not possible. It's not possible. Yes. Yes. Yeah.
Successive blowups is also a goal.
Yeah. Yeah, like if you use the successive blowups, like if you just blow up a one graph, then you'll get another graph. Again, if you blow up this graph, then another graph you'll get, but these two graphs will not be isomorphic.
Another question. As you can blow up the vertices one by one, so I wonder, is this PG a factor as a product of as many vertices as you have in the base graph? That is factor.
The PG factor
Uh-huh.
to number of pieces. Same number of pieces.
I think no. Yes. Okay, I'll think about this, but I think answer is no. Yeah. So in the next few slides, I'll talk about some other properties of this polynomial. So remember the polynomial pk2. Pk2, this is a multivariate polynomial. Now let me specialize these two univariate polynomial. Take r equal to s equal to n. Then the univariate polynomial equal to is 3n square minus 8n plus 4. And so, and it clearly factorizes. So it is real rooted. So this is for K2, but I can also blow up the complete graph on K vertices. And if you can check that if you take the univariate polynomial UKK, then again you get a real rooted polynomial. Now the question is it real rooted for every graph? And the answer is yes, but far more is true. Real rootedness is one variable manifestation of more powerful and general notion called real stable polynomials, and recall that a multivariate polynomial with real coefficients and complex argument is called real stable if it is non-vanishing in the upper plane. And the blow-up polynomial PG is real stable for every graph G. And here note that from now onwards, I'll treat this polynomial as a function of complex arguments. So the point is real stable polynomials are focus of tremendous recent research, primarily due to the work of Brochet-Brandon, who proved the far-reaching generalizations of Legge-Purcell program and proved three long-standing conjectures of Charlie Johnson using this polynomial. And these progresses are then taken forward by Marcos Pilman-Sivastava in proving the Cartesian-Singan conjecture and to prove the existence of bipartite Ramanujan graphs, infinite families of bipartite Ramanujan graphs. So the polynomial that I mentioned provide a new examples of real stable polynomials, and that arise interestingly from graphs and distance matrices. Now, let me go beyond real stability. So I remind you from very first result, I mentioned that the blow-up polynomial has this as a constant term and the linear term is given by these things. And this shows you, this already shows you immediately that this polynomial does not satisfy two desirable properties. Clearly, there is a the coefficient of constant term and linear term are of unequal signs. So this is the first property. And to bypass this, one can consider PG of minus Z, then this minus sign goes inside and the signs are equal. But one must of course check the higher order term, the quadratic term or the cubic term. Are they also same? Similarly, there is a constant term and the linear term. So the polynomial is not homogeneous. And for this, there is a standard trick of homogenizing the polynomial. And if I want to bypass both of this operation, I have to take minus sign inside. Now the question is, why do I want to bypass these one or two obstacles? The stable polynomials with these additional properties were studied in even border settings by Brochet-Brandon Leggett, and they call it strongly Rayleigh polynomials. That is, all coefficients are of the same size, same sign. And the homogeneous stable polynomials are broadly studied as Lorentzian polynomials by Brandon and Hu. And they also studied by Vincent Anari and Anari. They called it completely log concave polynomials, and Gurbitz called it as a strongly log concave polynomials. Now the question is, if we homogenize PG at -1, for which graphs does this yield a polynomial in this class or this class? And our next result exactly characterize this polynomial. And answer is, interestingly, if and only if all the coefficients are of same size. So answer to both of these questions are same class of polynomials, and they arise from a very familiar class of graphs, that is completely multi-partite graph. So given a graph G, define its homogeneous polynomial exactly the way I told you, and the following happens. The polynomial that I mentioned is real stable if and only if all the coefficients are of the same sign, and if and only if consider this polynomial without Z0 but with minus sign and divided by PG of -1, -1, -1. That is the sum of all the coefficients. So, so you get a polynomial whose coefficients are non-negative and add up to 1, and this forms a probability distribution. And the claim is these things happens if and only if the distribution is strongly Rayleigh. And all these are equivalent if and only all these are equivalent to the graph G is complete multi-partite graph, which is same as saying that blow up of a complete graph. So we provide a novel characterization of complete graph in terms of real stability. In the last part of talk, I'll discuss some combinatorial abstraction of this.
So related to real rootedness, do you get some type of interlacing roots if you consider different graphs? Let's say you take some deletion or contraction in G. Do you get some type of interlacing phenomena for the roots of the corresponding blow-up polynomials?
I don't have an exact answer right now.
Okay, that might be something
Yes,
to
yes,
look into.
yes. I'll think about it. Yeah. So yeah. So in the last part, I'll discuss some combinatorial extraction of these results called delta-matroid. And recall that a matroid consists of a finite set E called the ground set and a family of subsets of E called the independent set, which is closed under the taking subsets and independent set axiom property. Okay, so here are the some examples of matroid, and first one is known as free matroid, and here the independent sets are all subsets of E, and if independent sets are the of if independent sets are all subsets of E of some size less than equal to K, then we call it a uniform matroid. And the third example is a matroid from linear algebra. Let E be a finite subset of a vector space, and we define a matroid on E by taking the independent sets as linear independent subsets of E. For example, we can take E as the columns of a matrix. So now, instead of taking linear independent subsets, if we take the independent sets as the basis of column space of A, then it satisfies these additional properties. And this is known as symmetric exchange axiom. And if a for a finite set E and family of subsets of E which satisfies this axiom, these two together is called delta-matroid of G. Here the subsets are called feasible sets. And this the delta-matroid was first introduced by Projesh in 1987 as a generalization of matroid. And a delta-matroid is a matroid if the feasible sets all have the same cardinality. And here is an examples of delta-matroid. So like if you take a symmetric or skew symmetric matrix of size n, and you define the feasible set F is as follows. Take F is a feasible set if and only if the determinant of principal submatrix of A corresponds to F is non-zero. And Projesh shows that with this system, this provides a delta-matroid, and which is called as a linear delta-matroid. Now the question is, so far we have discussed about real, stable polynomials and delta-matroids. Is there any connection between these two notions? And this was a result by answer is yes, and this was a result by Brandon from 2007. So given a real stable multi-affine polynomial, the set of monomials in P forms a delta-matroid with this ground set. Now remember that our blow-up polynomials is real stable and multi-affine. Thus from PG, we can obtain a delta-matroid, and in fact far more easy, this delta-matroid is linear. And we call that as blow-up delta-matroid and denoted by MMG. Now look at this blow-up delta-matroid for G as a path graph on 3 nodes. This is exactly same as this. Now, here this coefficient here the coefficients of monomial of third degree is 0 because this is a blow up of an edge, and this is also infeasible because this is a copy of a same vertex. Now the question is, also more generally, one can verify this. This inequality holds for small path graphs on path graphs PK for small values of K. Now the question is, does this inequality holds for all values of K, or an independent of 1? Does this right hand side delta side is a delta-matroid for all K? And here is our result. The right hand side, this right hand side is an interior delta-matroid for all K, and it is equal to a blow-up delta-matroid if and only if K less than equal to 8. By explicit calculation, one can show that this is not a feasible set for a delta-matroid on blow-up delta-matroid of path graph for K greater than equal to 9. So in particular, for K greater than equal to 9, this left hand side is a proper subset of the right hand side, and this right hand side gives a different delta-matroid. Now the question is, can this right hand side delta-matroid generalize to more general graph? And this turns out to be hold for tree. And okay, how much time? Okay. So, okay, I'll maybe skip this. Okay. So here is our, okay, I'll just, so now just look at this. I'll explain why this is an infeasible set. So this is an infeasible set because this is a blow up of an blow up of an path graph. So it's the coefficient. So the coefficient in the of third degree in the coefficient of ni plus 1 ni plus 2 in the blow up polynomial is 0. So and so more generally, if we take any tree containing two leaves with common parent is a blow up. Now, if we set all such subsets of nodes to be infeasible set, does this gives a delta-matroid? And answer is yes. So before this, we need a basic definition. So recall that a Steiner tree Ti of a subset of vertices I is the sub of tree is the unique smallest subtree containing I. So suppose T is a tree and define a subset of vertices I to be infeasible if the Steiner tree Ti has two leaves with which are in I and have the same parent. Then the remaining feasible subsets form a delta-matroid. Okay, so we provide a novel delta-matroid for each tree, and we show that that construction of this delta-matroid does not extend to for more general graphs. So now there is a potential question: is there any connection between these two delta-matroids to any other known delta-matroid, any other known combinatorial delta-matroids? So, and here is the archive link for the full paper.
Thank you very much. There are questions.
Hi, thanks for the great talk. I was curious about your blow-up polynomials. You write them as the determinants of these sort of ever-growing matrices. Is there a formula for your blow-up polynomials in terms of as the determinant of like a linear matrix in your n1 through n?
Yes, yes, there is a formula. So we defined a modified distance matrix, something is called. So which will be a distance matrix, and in the diagonal instead of 0, we put 2. Like all the diagonal entries will be 2. So using this, we defined a so this suppose this blow up of each vertex is n1, n2, n1. Okay, so the determinant of this blow up is determinant of I plus I think this modified distance matrix times, if we define this as a diagonal matrix with this diagonal entries n1, n2, nk times this.
What's n?
This n is a diagonal matrix whose diagonal entries are n1, n2, nk. And these numbers are the like we blow up the each vertex. Like n1 is blow up with a n1 first vertex is blow up with an n1 different copies. Similar. Yeah, or m is a like this d is a distance matrix plus a diagonal
This might so this determinantal formula actually might give the sort of interlacing might give you some of the nice interlacing that was asked before. It's great. Thanks.
So this distance matrices, can you add some weights to the edges? You get like a weighted version of this.
Yeah, so we proved this result in this result we proved in full algebraic. Even like we can put a weighted, we take weights from a arbitrary commutative ring also.
And you get stability in that setting also for like real positive weights.
Can you repeat this?
Do you get stability, this real rootedness for when you have the weighted version of the?
Yes.
Oh, nice.
This metric spaces.
Is there a further question?
Thank you. Very nice talk. I was wondering, if I hand you a polynomial, can you tell if it's about a blow-up polynomial of a graph?
Sorry.
If you're given a polynomial, is there a straightforward way to tell if it's a blow-up polynomial of a graph without testing all graphs of the right size?
Yes. So if we get so the polynomial must be multi-affine and real stable, and from this, I think we can construct a graph.
You can construct a graph.
Graph, yes.
Yeah.
So I was wondering if there's, so I mean, since there was this discussion on, you mentioned deletion contraction, I was wondering if, and this polynomial is multi-affine, if there's any relation to multivariate tut polynomial which is multi-affine in some of the variables.
Multi-affine in
So there's a multivariate version of the tut polynomial due to so-called.
okay. So I think he may answer. I don't have an idea.
Thank you.
So it seems that all questions have been answered for the moment. So let us thank our speaker again.